Okay, as usual, let's start with the announcement first. You definitely have received my announcement earlier, so we have moved your test to next week. So please make sure go to the lecture site and look at the semester calendar. I have updated it. So we are now here on the 28th, and your test will be tomorrow. Sorry, not tomorrow, next week, Thursday, okay? And then, sorry if I scare you. All right, it's not tomorrow, don't worry. All right, so what about, okay, quick reminder. For your written test number 1, if you want me to go over the question with you, happy to do it, just drop by or make an appointment. For your lab number 2 solution, I may not have time for today. I really want to finish off what we left for the initial model, but if I can, I'll try to do that maybe on Wednesday. So I think studying the lab 2 solution can also help for your programming test 1. And for your programming test 1, that's going to happen next Thursday. Not the coming one, but next week. I'm going to give you the guide by the end of tomorrow, and then just to lay out the policy. Okay? And also the practice question, I'll also give that to you by we meet up on Thursday. All right? That'll be the plan. Okay? You definitely got enough time to get prepared. At the same time, if you really want to just review very quickly about what you did in lab number 1, that will also help for your programming test 1. And I'll speak more about it once the guide is released. Do you guys have any question about the course in general? We okay? All right. All right, so it would be very worth our time to do some very quick recap about what we cover up to before the reading week. So everything I put on the page is something you are supposed to have already learned. If you haven't, you want to catch up. Okay, let's do a very quick walkthrough about what we learned about the bridge controller initial model. We introduced the idea about requirements documents for each system. You want to make sure you know what the E descriptions are and also what the R descriptions are. And for the initial model, we are handling just one single requirement, which is about the number of cars on the bridge and islands is limited. That's what we're handling, right? Just always remember there's certain requirements you are modeling against to. And then we got this initial model here. We got static part, which contains the constant and axiom. You may have more than one in general. Also, you got the dynamic part, which contains the variables and also invariant, right? And also, we got 2 events over here. At the moment, these 2 events have the true guards, which means for these 2 events to occur is unconditional. They're always enabled. Okay, just remember. And that's the diagram you should always remember about initial model. That's how you remind yourself about the details. All right, let's go a little bit further. And these are the stuff that we formulate to make sure we are able to do some formal analysis of our initial model. And we'll definitely continue with it. Before that, let's see what we have learned. This is something called a sequence. Okay? And formally, it's really about hypothesis implies G. And this implication here may or may not hold. This is something you want to discharge by yourself on the paper. All right? So what I will do is I'm just going to put a question mark over here. So that means it may be a theorem or it may not be. When it is not a theorem, you will have to review what's really involved and change something. That's the exercise we will do today and on Wednesday. And for example, why would it be useful to study about the sequence? It's because in order to prove the model is actually correct, one very important aspect is to make sure the invariants are always preserved. The way to really prove that is about formulating this particular sequence. And it's called a proof obligation. Proof obligation. And that's the only one we have learned so far. Well, I would say arguably that's the most important one you want to remember. Right? If you remember the layout for the proof obligation, in order to prove that a certain invariance, you can see is index I. So it can be 1 and can be 2. And then it's going to take the effects of certain events, and the guard of the event is going to be on the hypothesis. Right? That's what we said about before. And you want to make sure you really understand the difference between this one here. Let me make it a little bit thicker. This one here versus this one over here. This is what we assume the invariant being held in the pre-states. This one here is about the invariance being held at the post-states. In order to derive the invariant at the post-states, we have to do some replacement or substitution by the before-after predicate of the events, right? Everything I'm saying here has been set already before the reading week. If you got any trouble, please review the lecture or just come to me, so we'll clarify. But for now, that's good. And once we have formulated the invariant preservation, this will be one example, right? And we talk about the naming convention. So about invariant preservation, and we're saying for invariance, just number one. We only deal with one invariant at a time. And then we got this particular events, which can be ML out or ML in. But for this one, just ML out. And that's the sequence you would like to prove. In order to prove the sequence, we introduce another notion, which is called inference rule, right? That's basically towards the end, before the reading week. Inference rule. Do you guys remember the informal or the meaning of an inference rule like this? I think this will be a very nice transition to the lecture today for us to continue. Anybody? If you remember what this really means. Either formally or informally. Adnan. That's pretty much it, right? Yes? Okay, let's now revisit very quickly. For this one here, formally, you can say A implies C is a theorem. It's more like an axiom. So you can apply that without proving the inference rule. And number two, how do you understand it? To prove C at the bottom, it is sufficient to prove A at the top. Right, so these are the two meanings you want to keep in mind. And we're going to use this a lot today to really reinforce your understanding. And I think maybe you want to also, once we get to the proof, it may seem like arbitrary, but I would say you would just have to try different paths to really finish the proof. So I'm going to assign some exercises for you guys to try. But I would say in general, you have to identify the pattern that's really indicated at the consequent over here. Once you can identify the pattern, you want to see what would be the antecedents I want to prove instead. And that hopefully will lead you to some axiom inference rule at some point. Right? But that's a general remark. But we're going to see many examples. And two more things. We talk about before-after predicates for each event. For example, this one here, if you recall, before-after predicate is m prime equals n plus 1. Right? We spoke about it a lot. Make sure you review. And also example inference rule. We're going to learn about close to 20 inference rule towards the end of the course. We'll go set by set. The first set of inference rule, I already made it available to you. In case you don't know, I'll show it to you. You can go back to the lecture site, and then you can see under here, the notes. Right? You can see example inference rules, number 1. All right? We're going to hopefully introduce number 2 as well today. Right? That's what we talked about last time. Okay? In case you're still very struggling about how to interpret each inference rule, you can maybe go back to lecture recording right before the reading week. You can maybe have some brush up. But today, we're going to see how we can apply the inference rule. I can tell you what the trickiest thing is. At the end of the course, you will have already learned about 30 inference rule. And let's say given a sequence to prove, you don't necessarily have to apply all the 30. No, very unlikely. You only apply part of them. In that case, how can you judge exactly what to really use? I think that's really up to how much practice you have done before the actual assessment. Right? Anyway, so I'll try to go over the proof very slowly with you, just make sure at least you got the basic understood, and then you can do the exercise. All right? Okay, so that's about a very quick recap about what we have learned in the course so far. Do you guys have any question? Any part you want me to address a little bit before I move on to the new stuff? All right? Okay. What I would like to do is to say this. If you recall what we did the last, we'll talk about the inference rule, and now what we would like to do is this. We got 4 sequences over here. So where do these come from? They come from generated the generation about invariant preservation, if you recall this particular rule. Right, this one here, because how many invariants do we have? We got 2 invariants. How many events do we have? We got 2. So 2 times 2, we got 4 sequence, right? We explained that before the reading week. So we got 1, 2, 3, and 4. In order for us to consider the model to be, I quote, correct, at least invariant should be preserved for every event and for every invariance. So we got these 4. And let's now try to prove them one by one. If we can prove each one of them, that's good news. And we're pretty much done with the initial model. If we cannot really prove some of them, that means we might need a little bit more work to fix the model to really make sure we can redo the proof and get it discharged. That'll be the workflow. Okay? And since you guys are just beginning to learn about how to do proofs, I'll give you a very big hint, but don't assume that's going to be the case in the assessment. Here, I'm telling you exactly what you might want to use, ultimately. Right? I'm giving you 4. These are the most relevant ones. And always keep in mind, monotonicity rule will be your best friend. Because this one is telling you, if you're given so many hypotheses, for example here, to really prove this sequence here, you don't necessarily have to use every hypothesis. You can only be selective. Just choose the one you think you might need. And you can, for example, if you find that you're given so many H1 and H2, you can simply drop H2. Only use H1 to continue with the proof. Right? This will be the #1 most frequent inference rule you have to apply at first, most likely. All right? And then you got other things over here, and here, and here. And we're going to see how we can use them. Okay, let's go one by one. All right, let's take a look at this. I want you guys to just focus on that, just for one moment. Try to convince yourself what's really to be proved, what can be assumed, and what's really to be proved. Stare at that for just one moment. And answer the following question to yourself. What would be the relevant hypothesis for me to use? Do I really have to consider all the hypotheses? Okay, one moment, and then I'll point to Adrian. All right. Adrian, what's your insight?
I think the most relevant hypothesis would be the n is in the set of natural numbers.
Mm-hmm. Sure.
Because then all the proof basically becomes is just n is a number. Prove that n plus 1 is a number.
Exactly. Very good. Right, so guys, in case you haven't seen that, this is what we want to prove. So you always can work backwards. Think about this is your goal. You want to prove this. What can be the relevant hypothesis or hypotheses that's going to help you? In this case, it might be quite obvious. Given that n is a natural number, I can easily argue n plus 1 is a natural number. Guess what? This is one to the rule. P2. That one is saying, in order to prove this sequence over here, it is sufficient to prove nothing, meaning that this is automatically provable. So here, I want to do one thing here and tell me if that's really correct or not. Okay? Can I simply say, by P2, I prove it automatically? Ryan. Monotonicity first. Don't worry, it takes some time to get used to it. Yeah. Mm-hmm. Okay, very good. So guys, the reason I'm mentioning about this is a common mistake. If you say, okay, I got n here, okay, let me just circle that. I got this one here, I got this one here. They somehow correspond to exactly the P2 over here. So I can conclude by using P2. Done. Not really. Because in order to apply P2, everything should match. You can see here, this guy here matches this guy here. That's okay. But the hypothesis over here is only n is a natural number, and n is a natural number. But what about these two? They are not relevant. They are not part of the pattern. So you cannot just use it directly. All right? So I'm going to put a cross over here because the too many hypotheses All right? So as Ryan said, what we should have done is like this. Number one, we should do monotonicity. You can think about H1 is what we want to keep. This is a bit like a H1. The remaining part is like a H2. Okay, so what I will do is I'm going to apply monotonicity. After that, I'm going to get just n is a natural number. And then n plus 1 is a natural number. This will be the sequence I can get after applying monotonicity. And that one there very nicely corresponds to P2. All right, so I can use P2. That'll be the proof. If you are lost already, please let me know right away, because we're going to see some more complicated proof today. All right? Okay? If everybody's okay, that's a good sign. Let's try this one here. Oh, let you focus. Do you think this might be provable? Somehow we want to say n minus 1 should be a natural number, intuitively. If I say n minus 1 is a natural number, that means n minus 1 should be larger than or equal to 0, right, informally. Is there any hypothesis over here that's going to help me to say, oh, that, let me go a little bit further, just to be precise. This is my thinking process. So this one is telling me n minus 1 should be larger than or equal to 0. Equivalently, n should be larger than or equal to 1. Or you can say n larger than 0. This is indeed what I want to prove. Is there anything in the hypothesis that's going to help me? Right? That's what you want to think. Sarah? You mean this one here? Yeah. So remember, for natural number, it starts from 0. So if you claim that this expression here is a natural number, so that expression there must be larger than or equal to 0. And then I move the minus 1 to here, so that'll be plus 1. Right? So that's why. Okay? All right. So it seems like there's nothing here that will be sufficient for me to conclude n is larger than 0. The closest one I might get is something like n is a natural number. But if n is a natural number, what does it really mean? It's larger than or equal to 0. Does larger than or equal to 0 imply larger than 0? Not really. Right? So that's why this is unprovable. All right? So, but I can make some progress. So what I would do is like this. I would say by applying the monotonicity, I can try to keep just this sequence over here. All right? And then I'm going to get n is a natural number. And then, does that imply n minus 1 is a natural number? Apparently, this is not really true. So I'll put a question mark here. That's not really. No inverse rule is applicable. Right? Even in general, that's simply not the case. If I know larger than or equal to 0, I cannot argue larger than 0. Okay? Let's think about, in this case, how can we make it work? This is something I want to prove, so I don't want to change what I want to prove. Okay? This comes from the invariance, so I don't want to change that. Is it possible for me to change this part over here to make it more relevant to this one here? Okay? I want to point out to you guys about this. Okay? Usually, you can see this is an invariant I want to prove. All right? And invariant is already fixed. Axioms are also fixed, usually. But you can add more axioms if you need to. Another part you can touch is by adding maybe more guard for the event that we're considering. Because for this one here, we're considering MLN, for example. In that way, maybe I can add some guard to really make it work. Ryan? You mean this one here? Yeah, of course. This one could be a possibility, but this one is actually come from, if you remember less than equal D, that's an invariance. In this case, yeah, I think what Ryan is suggesting is also possible in general. Whenever you have some unprovable sequence, every part is a candidate for you to change in the model. But in this particular case, you want to think a little bit more into what's being proved. For MLN, we know that every time we want to really have some car that goes back to the mainland, we want to deduce the number over here. But somehow we say that this particular event is unguarded. So that itself is actually not appropriate. So that's why in this case, we will choose to really change this part, right? Yeah. Okay. So I just want to say, for this part over here, for the hypothesis, right, may need to add a guard to MLN. All right. Okay, are we okay with this? It is some unprovable sequence that has to do with the MLN. So we thought maybe it would be nice to really change the guard. If we try to add some guard into MLN, that means rather than just having true over here, we're going to add some guard over here as the hypothesis. That's going to help us. All right? That's something you will see on the slides. All right, let's try one more. Okay? This one here, if you look at that, okay, this is what we want to prove. I can tell you that the conclusion is this one here is still unprovable. But let's make it a little bit more focused. Since what we want to prove has to do with N and D, all right? So this seems a little bit relevant, right? If we know that N is less than or equal to D, can we conclude N plus 1 is still less than or equal to D? No, obviously, right? So for example, if N is already equal to D, in that case, plus 1 is going to make sure it's not less than equal to anymore, right? Okay, so for this one here, I'm also going to apply, first of all, the monotonicity and show that we actually get stuck. Okay, this one here would be N less than or equal to D, N plus 1 less than or equal to D. Okay, this one here, we also cannot prove it. So I'm going to put question mark and question mark. Okay? And for this one here, we want to make a note. Since this proof obligation has to do with ML out, so we might just be able to add some guard to ML out to really add some hypothesis to make it work. Okay? May need to add a guard to ML out. And if you recall, at the moment for ML out, it's unconditional, no guard. If I add something over here, I'm going to add something to this part over here, for sure, right? That's the idea. But we'll get to that in a moment. What about this one here? Okay, this one, is it provable or not? Intuitively. Again, what we really want to prove is this guy over here. Go ahead. It's provable. Okay. Which hypothesis is relevant? All of them? In some way true, but we can maybe just leave one of them. Yeah, go ahead, sorry.
Sorry, so it's the third one.
The third one, yeah. So guys, I would say give you some tips. Usually, any hypothesis that have to do with the typing, if you can find something that's a little bit more specific about relating different variables, you might not need to consider them anymore. Because in this case, we are considering N and D. So we really want to find some hypothesis that's going to relate N and D. So that's why we only keep this one. Okay? Let's see a little bit more. If N is less than or equal to D, N minus 1 less than or equal to D. That makes sense, doesn't it? However, which inference rule can we use? Here. The second one, decrement, right? But be careful. Let's now compare very carefully. Okay? Sorry, it's a little bit small. I'll try to make it just enough. This part here and this part here, do they really match? Oh, guys, be careful. less than or equal to, less than. Unfortunately, no. Also, less than or equal to, less than or equal to. This part actually is fine, but this part over here doesn't really match. If the pattern doesn't really match exactly, you cannot apply it directly. You may want to do some massaging before you can apply it. So that's why this proof here is going to be more complicated than before, but we're going to do it together. Okay, first of all, I want to say something right away. If I simply say, by applying decrements, and I prove it. No, not yet. Cannot apply it directly, for the reason I just explained to you. Okay? What we would like to do is like this. N less than or equal to D versus N less than or equal to M. This part is fine. N minus 1 less than or equal to D. And also N minus 1 less than N. The difference is, right, let me write it out. N minus 1 less than or equal to D versus N minus 1 less than M. Okay? If you think about what you should do, somehow this M here should be instantiated with D. The N here will just correspond to the N over here. But we are having trouble on this. In this case, we can do a little bit arithmetic manipulation. What we can think about is like this. This guy over here, by the basic arithmetic, it would be N minus 1 less than D, or N minus 1 equals D. Do you guys agree? Less than or equal to, right? It's either less than or equal to. I'm just splitting this inequality here into two different disjuncts. That's what I have done. Go ahead. Mm-hmm.
Just keep that. So do we just assume that n is a natural number and d is a natural number?
Yes, indeed. So basically, yeah. So these are already. So when you say this already here, well, thinking this way, this is what you want to prove, right? It's relating n and also d. So you want to find something that's going to help you relating these two variables. So that's why keeping this will be enough. Yeah. Mm-hmm. All right. So guys, this is a very important insight into this problem here. Number one, you should really know why we cannot apply decrements rule directly. It's because this part here doesn't really match. It's really important. Okay. What we want to do is, if we can somehow split this part here into these two parts, and then this part here is going to match this part over here. But there's one more problem. This part does not stand alone. It is part of a disjunction. Is it possible to only consider this disjunct without worrying about the other one? Well, that's what this will do for you, right? This rule over here is telling you, in order to prove something that's a disjunction, what I can prove instead is just prove one of them, the left disjunct. All right, so this one here is definitely more complicated than before. So guys, I want to make sure you follow. All right, let's try, and then I'll take your question. All right, so let's see how we can do it. First of all, I'm going to apply some basic arithmetic. Whenever you want to apply some basic arithmetic, just use ARI. ARI is referring to basic arithmetic. So let's say in the later test or in the exam, if you really think the property you are trying to use to rewrite the expression is very basic, you can write ARI. However, you don't want to overuse it. Sometimes what's obvious to you may not be so obvious, right? So you got to be careful. I would say this one here is definitely fine. Okay? So what I would do instead is like this. After this, I'm going to have the same hypothesis, n over here, also n less than or equal to d, and then n minus 1 less than d, or n minus 1 equals d. Okay, this is a very critical step. We want to make sure we did right. Okay, recap. By applying the arithmetic, we basically rewrite this one here. Oh, sorry. We basically rewrote this one here into this one here. Are we okay with this? Again, you guys might think, why everything seems so arbitrary? So I would say if you're given some new proof to really try, you got to think about different possibility. It's really hard for me to tell you exactly what to do in general. I can only just give you examples and tell you some insight. All right? All right, after this, we are getting very close. What we would like to do is like this. This part over here, okay, let me just say this. This part over here is having less than. This part here is having less than or equal to. So we're getting very close. Okay, so what I would like to do now is, why don't I try to drop everything that's not relevant? Okay, I don't need it. So what I would need to do is I'm going to apply monotonicity, which is going to leave me only with this and, okay, or n minus 1 equals d. Okay, this is, we're getting very close. Okay, this one here, oh, sorry, I can draw better. Okay, this one here. Okay. Okay, by monotonicity, okay, so we only got this one left. All right? But we want to somehow get rid of the other one. We want to leave only this one here. To do that, we have to drop this. To drop that, we have to use this one here. You can try to look at them side by side. This one here is like P. This one here is like a Q. You can see there's a disjunction in between. What I want to leave alone is this one over here, the left. So that's why we're going to apply the OR R1. If I want to take the right-hand side, it should be OR R2, which is the other one. Right? You want to make sure you really review the inference rule to make sure. All right? Okay, one more step. I'm running out of space, so I'm just going to say, after this, if you don't mind, I'm going to put it here. Okay, after this. I'm going to have just another one, which is OR R1. So I still got n less than or equal to d, and then n minus 1 less than d, right? That's what I got by applying this, right? So by applying this, so now I got this and this. Do they match? Less than or equal to? Less than. Perfect. All right? After that, I can simply say, to prove it, by applying decrements. That'll be the last step. But of course, you look at the slides, it will also show you this sequence here. But you ought to know how to really apply the steps very carefully. You don't want to jump. All right, so that's about a very thorough discussion about each one of them. Are you guys okay with all the proof obligation here? Question? Yes.
I know you clarified this before. Would you mind reiterating why you could omit the types of TNF?
Oh, okay, sure. You can think about, okay, thinking this way. If you look at these three over here, think about what you want to really prove. In order to prove this one over here, I need to find out some hypothesis that will actually involve N and D. In that case, that's why I will just need this one over here. And ultimately, I really want to use the decrements. If you look at decrement over here, this one here doesn't really restrict about N and M being natural number. So in order for me to ultimately apply this, I really don't need these two. All right? Yeah, okay. Okay. All right, go ahead. Well, to be 100% honest with you, to save time, when I create a slide, I just look at the textbook to see what they have to prove, and then convince myself, oh, yeah, that's right? But if you're really given a new sequence to prove, I would say you will just have to try, right? I would say this is how I think based on my experience. Number one, start by looking at what you want to prove. Start by that. And then from there, try to look at the hypotheses over here to see which one might help you on that. And when I say help, that means look at all the inference rules you have over here and see how you can use them one by one. Mm-hmm. I would say in the actual written test, I think for your written test number 2, the proofs that you're going to have to do will be rather similar to what the examples, very similar to the example we did in class. So if you really follow through what we did in the class, you should be able to do them. Okay? But in the actual exam, you might be given maybe some new proof that you have to discharge. In that case, I will allow you guys to maybe make some data sheets for your exam. So you can put all the inference rule that you might need on the paper, and then you got to decide. Yeah, so guys, think about what we're doing here is pretty much like what you did in 1090. So is there really a general pattern for you to do all the proofs? It would be nice if such pattern exists, but it's no. Right? So if you really want to prove something creative, I think it's just trials and errors. No way around. All right. Some question here, right? No? Oh. Guys, any clarification needed? This is so important for you to get. I think hopefully we can get to one more, even more complicated proof for today. Right? But that's really important for you to digest and then do some exercise. All right? Okay, so what's the conclusion from this? The conclusion is, since we got two things that are unprovable, you can see this one here is unprovable. This one here is also unprovable. So we are not really done yet about judging, about verifying our model. Not yet. We got to fix something. The ultimate goal will be we want to maybe fix the MLN and MLOut events in such a way that we will be able to discharge this one here and this one here. After that, we are done. All right, that's a roadmap. Let's just go back to over here. All right, that's something we just spoke about. And you will see the more organized proof in the slides, right? And that's the one we just did. And a very important mental exercise for you. Over here, I'm using OR1. What if I use OR2? Is it going to help? Think about this question here. The obvious answer would be maybe no, but you want to know why. Okay, again, the exercise you want to do very quickly is, here, rather than applying OR1, what if I apply OR2? What's going to happen? Right? Think about it. All right, after this, so we want to fix the design of the event. Specifically, we want to add guards. Okay. Initially, because both the MLOut and MLN, they simply got true as their guards. As I said before, as a design tip, if you simply got unconditional events, it's usually a no-no. You don't really want to do it. You want to have some guard. Okay, so to really fix it, this will be the fix. All right. And I will go back and give you some comments. Okay, let's see, why do we need this MLOut, M less than D? Okay, it's because, oh, sorry, not here. If you recall, let me try to see if I can, okay, let me just copy this first. Okay, this is something that we didn't prove. Okay, sorry. Let me just put, this is something that didn't prove. Also, this is another that didn't prove. Okay, let's have more connection for you. Sorry, just give me one moment. I'll clean it up very quickly. Okay, so we don't need that. Okay, for both of them, oh, did I actually got, oh, sorry, I think I copy ML out. Sorry about that. Copy the wrong thing. Let me do it again. Yep, that's the one. So this one, ML, what am I doing? Let me do it from scratch. The first one that's not a proof is this one here. And then I'll show you what it really means when we add a guard. Okay, this is the first one that was not proved. The second one that was not proved is this one here. There we go. Okay, and over here. Okay, there we go. And then let me clean this up very quickly. Okay, it should be rather clean. This unprovable sequence over here has to do with MLN, which currently has just true guard. And you can see every time you're trying to do MLN, the before-after predicate is going to decrement n by 1. And how can we be sure n minus 1 in general will still be a natural number? That means after this, how can we make sure n is still a natural number? How do we do that? That is to make sure you can only do the decrements when n is not too small just yet. What will be the smallest number to make sure n should be? After decrementing this, it can still be a natural number. 1, not 0. Because if n in the pre-state is actually 0, 0 minus 1 is going to be minus 1. Right? So n should be at least 1. All right? So that's why the first guard that we're going to fix, as you can see from the slides, is over here. N larger than 0. All right? So what we really want to do is to introduce over here to say when n larger than 0. Again, n larger than 0 is to make sure after n minus 1, it will be a natural number. So what's going to be the consequence of doing this? If you try to add n minus 1 as a new guard, that means over here, you're going to put n plus n larger than 0 as a new hypothesis. Why? Because if you remember the proof obligation rule, you have to include the guard of the events. Since we add a new one rather than true, so it has to stay there. So guys, you really want to make sure the picture is clear to you. All right? All right? So this will be 1. And what about another one? Another one will be for ML out. If you look at this one here, that also was unprovable before, what we want to make sure is n plus 1 is still less than d, less than or equal to d. If you look at ML out, the before-after predicate tells you that it will always increment n by 1. But how can we be sure after this it will still be less than or equal to d? This symmetric way. You want to make sure when ML out was actually enabled and just about to do plus 1, it should be strictly less than d. That's basically what you're going to put. All right? So that's why if you go back to the slides, it will tell you that it should be strictly less than d. All right? So we're going to add a new guard over here to say when n strictly less than d. And what will be the consequence after adding this? So we're going to add a new hypothesis over here, n less than d. That's what we will do. All right, are we okay with this? Right? That's about the insight into how to look at the sequence that's unprovable. And then look at what's the corresponding events that should be responsible for that. And then try to maybe strengthen the guard accordingly. That's what we have to do. Okay? And the next step is, given that we have added 2 guards. So you can see here, they are reflected in the sequence that's automatically regenerated. This one here, this one here, this one here, and this one here. So these are the new guards that we just added by fixing the model. And now, all these proof sequence will be provable. And how do we prove them? That will be the exercise for you. All right? And I'm going to post a walkthrough video to help you, but I think you guys should really try first before you're convinced. All right? I'm going to recap very quickly, and then we should take a short break, and then we'll continue. Okay? So this will be exercise. Guys, let's recap about what we have talked about since the last 40 minutes, okay? And then we'll give you a break. Given some model which contains static and also dynamic. Static, which contains the constants, the axioms, and we got variables, and we got invariants. Right? This is what we are given, always. And the question we are asking is this model correct? And to be more precise, as far as invariant preservation is concerned. So now we're only considering whether the invariant can be really preserved. There will be other concern a little bit later after the break. Invariant preservation. Okay, so what we do is we're going to turn this model into sequence. Formulating the proof obligation of invariant preservation. And that's exactly these four initially that we talked about. 1, 2, 3, and 4. And we'll try to prove each one of them by applying the relevant inference rule. If there's any one of them that's not really provable, you have to go back to the model and see what to fix. In this case, since we are being very specific about about some events with respect to the invariant preservation, so the obvious choice will be to fix the event guards. Okay? And then after this, any unprovable sequence means fix the model and then, one more. Fix the model and you want to regenerate all the proof sequence. Regenerates the sequence. You can see here, after adding the guards, we have to regenerate the sequence over here accordingly, right? And then try to prove each one of them. Proof again. This might be an iterative process you have to keep doing until you fix the model enough so that all the proof obligations are discharged with respect to invariant preservation, right? That's basically what we have spoken about. It's a very nice workflow over here to work things systematically and formally. Guys, any question? We okay? All right, think about it and speak to me if you need any help. Okay, I think you guys deserve a break. Before that, yeah, sorry, say it again. I couldn't hear you.
Go back to the last page so we can see the actual.
The last page? You're good? All right. Sorry, do you still have a question?
Doing it as an exercise, can we, I thought we were doing it as an exercise, so can we, keep on saying it? Whatever.
Okay, so let's now take attendance, okay? All right, so let's now let me start a class, and then you guys can get ready to check in. Okay. All right, check in, please. All right, if you got any trouble, any technical issue, as usual, I got a sign-up sheet there. All right, guys, we'll take a 2-minute break, all right, and then come back, and then we'll continue.
When it comes time for actually writing it on the lab computers, do we have to set up the manual post-tactic?
Not for programming test one. Okay. Not for that one.
And then I just wanted to clarify, like, the point of proving all of this is to reach to one of these final, like, inference rules?
That's the goal,
Yeah,
yes.
because these are terminating, right?
Mm-hmm.
Okay, yeah, that makes sense.
Exactly, yeah. If you think about if you're only applying these, there's still something else that's outstanding for you to prove. Yeah. So that's why you have to ultimately, yeah. So that's why I try to use a green to represent base cases.
Yeah, okay, thank you.
Okay?
I just have a question about the third proof.
Yes.
So when this happens, right, does this change the first guard?
Which one? This one here? That's the extra guard we added for these events.
So we don't change the previous guard?
No, we don't really do that. Oh, you know, this previous guard is actually, let me see, give me a moment. No, the previous one is not actually a guard. It's actually an invariance, right? You can see, okay, let me show it to you. Yeah, come over here. If you look at this one here, so we say that in order to formulate an invariance, you should really get an invariant at the pre-state, which will include n less than or equal to d. In the first version, the guard is simply just true for these two events. Right? So that's why we didn't write anything, because it's simply true. Right? But after adding that guard, we're going to add this one here. But this one is still the accident, so that's why we still should include it.
Okay.
Okay? Yeah. Yes?
Keep attendance open for a little longer. I missed this, like today's attendance by a couple seconds probably.
Oh, next time just do it a little bit more quickly, right? Why don't you just sign up here?
Yeah.
That'll be fine. That's Apple Pencil. You want an actual pencil. Yeah.
So I have the same problem. It says I checked in, but then I missed, like as soon as I joined.
It should be fine, I think. If you really want to double check, you can visit my office hour. I can double check the spreadsheets. It's actually online. You can check at some point.
Could I just like sign in? Sure.
That's cool, okay. That's fine.
Alright, that's good.
All right, let's resume in just one moment. Yeah, you'll find your name and then you can sign. It's sorted by last name. Okay. All right, let's get started again. All right, so before the break, we spoke about how we can modify the guard of the two events. These are the extra guards we just added, all right? And these are the regenerated sequence over here, and all of them are provable. So once you have done the exercise, I will recommend you to try before you look at the slide for solution. This will be something you are expected to do later, right? Just make sure you can do it. All right, if you got any trouble understanding about the proof, reach out. And let's now talk about another small issue. And this is just another proof obligation, but typically it should be rather straightforward to discharge. But let's talk about it for conceptual completeness. So if you look at that, okay, let me see this. It is like a proving by mathematical induction. Right? If you remember, before the reading week, I drew the analogy about proving invariance always being held to proving mathematical induction. What we just did before the break about preserving the invariance is like inductive cases. But what's really missing is about base cases, which are rather straightforward. But you should also know how to formulate them, how to prove them. I want to draw some very quick connection over here, very quick. When we talk about mathematical induction, right? So there are base cases, which we'll speak about in just one moment. You can think about for base cases, there's only one single state. Only a single state to prove. Think about this single state here is when all the variables were just initialized. Right after. Okay, let me just write it down. Right after all the variables initialized. Okay, that's something we'll speak about just in a moment. And what about inductive cases? If you think about what usually you write in the mathematical induction, you say assume that Pn, you want to show that P of n plus 1, right? That's really what we have done. You want to draw the following analogy. If you think about what we did, is to formulate these 4 sequences over here. Okay? Think about what's really happening here. Oh, okay. So what I will do is I'll try to draw a little bit better. All the hypotheses over here, they are like a different scenario about the pre-states. Different pre-states for event occurrence. So if you think about, we're just saying given some arbitrary state over here. When I say arbitrary, it's not exactly arbitrary. The state itself must have the axioms satisfied, and also the invariant satisfied, and also the guard of the event satisfied, right? That's really for us to consider different scenario. So given that this state here, we want to argue that by taking either ML out or ML in, we're going to end up with a state that still satisfies the invariance. So that's exactly this part over here, right? That's how you draw the analogy. Okay, let me put it here. So this one here is about all the possible resulting states. The resulting post states. And we want to make sure every one of them is provably correct to really preserve the invariance. All right, so that's how you draw the analogy between what we have done before the break and about mathematical induction. All right, so what's really missing? What's really missing is how do we make sure the very first state for all the variables to be initialized, they actually satisfy the invariance. So all we got to do is specify in your model, you should really specify something over here. Let's talk about a little bit about initialization. So it's represented by some events called init. Always the name. That's the name of the events. Just for initialization. Always called init. And then this left-hand side over here, we only talk about variable. Variable only. You don't really try to initialize constant. No, only variable. Variables only. And this right-hand side over here is very crucial to know. In some way, it simplifies the matter, but you ought to know why. Okay? When we talk about the initialization, this events occurs when this event occurs. None of the variables have been initialized just yet. Have been initialized. Okay, none. So that means as part of the, for the action over here, you should never say anything to do with the variable. So what do I mean? Let me write it down first and I'll show it to you. The right-hand side of this becomes operator should not refer to variables. Okay, let's think about this. If this is the initial states, so this is the init events. For this init events, there is the post states. Post states of the init events. Is there any pre-states for the init events? Not really, because that's when the system is first initialized. So here, there is no pre-states. So in order to specify what kind of updates you can have for the init, you can only mention about values that does not have to do with the pre-states. Okay? For example, what could be wrong? For the init, I'm going to put some example here. If I say n will become n plus 1, this is wrong as an init action because n here is referring to the n that exists in the pre-state, but there's no such notion about pre-states for the init events, so that's not good. Okay. All right. So, not appropriate. All right, that's what I need to mention about init events. Always just put some concrete values over here. For example, 0, right? All right, are we okay with the init events? Okay, it's rather straightforward. You just got to be careful about what you specify, especially on the right-hand side. All right, because conceptually, there's simply no notion about pre-states for the init events. Only the post-states, only. That's the special one. All right. Let's now try to talk about, given the init events, how are we supposed to prove that the invariant is established? How do we prove it? Okay. Very easy. Again, this is our model, and that's init events. And we don't really need to consider ML, MLN at this point, so that's why I'm not including them, but they should be there. Okay. So we still got our constant, the axiom, variables, invariant, etc. Okay. And this will be the rule about invariant establishment. We are saying that given all the axiom being true, we want to prove that the invariance by applying the effects of the init events is going to hold. Right? So you can see here, I'm just making some reference for you. I want you to compare the following. Compare with effects of a regular, or let's say non-init events. Okay? So here we're saying that for the effects for the init events, it only uses constant C. But what about for non-init events? You can also make use of variable, right? You can look up to the definition from earlier, but it's going to be something like this. It's going to be the effects E, which may use constant, but it may also use V, and also V, just V. Okay. I want you to compare that. Okay. That's why you just in the init event you just can put constant. You cannot put any variable. All right. Based on this, what proof obligation, what sequence can we generate to argue about invariant establishment? First of all, how many sequences do you think we need to generate? Let me give you a little bit hints. Before, when we talk about invariant preservation is only for regular events. We got 2 events over here. We got 2 invariant over here. So 2 times 2, we got 4. What about now? How many events do we need to consider? Just one, the init. How many invariant do we want to prove that it can be established? 2, 1 and 2. So 1 times 2, that means we got 2 proof obligation to be established. What are they? All right, let's try. This part here is just about axiom. Right, so what do we have? We got this one. That's the only axiom we have. So we got D is a natural number. Right, and then we want to establish the invariant 1 by 1. Right, that's the index I. Can be 1 and can be 2. Okay, let's try the intermediate value that will help you. So here I'm going to say n prime in the post states will be a natural number. Right, that's 1. Okay. And we got another one. We still got the same hypothesis over here. And then what about the second invariance? It would be n prime less than or equal to D. Are we okay so far about generating these 2? Okay, you can stare at these 2 proof obligation for a moment. How do we name them? So we'll follow the same convention. First of all, start with the event name, init. And which invariant? In this case, invariance model 0, number 1. And then it's about invariant establishment. Okay, that's the name. Similarly, for this one here, it will be init, invariant model 0, number 2. And then invariant establishment. Okay? You can see the common part is this part over here, right? Because axioms are the same for the same model. Finally, how can we replace this m prime over here by something that's pre-states? You have to look at the before-after predicate, which is just 0. M prime will just be 0, right? That's the before-after predicate. That means I have to replace this one here by 0, and this one here by 0. So these are the two sequences I will need to prove manually. Okay? Are we okay with this? Okay, that one's not too bad, right? Everything I'm explaining here, that's something we have done before for invariant preservation. Now, can we prove them? Let's try very quickly. All right, you can see this is 1 and this is 1. And for this one here, I'm even telling you what can be relevant. Okay? It's a very quick exercise for you guys. Tell me, for this one over here, what should I apply to prove it? Think about it, just for this one here.
I mean, that one, like, there has to be some rule that says, hey, the integer greater than 0. But, yeah, but just, I think I just start with this proof, right? Like,
What you're talking about is more like an informal thinking you might have. But if you want to do it formally, tell me what inference rule you would need to apply. Go ahead, please. Monotonicity. Okay. Guys, one thing maybe I should try to put on the exam. How do you pronounce monotonicity? Okay, maybe I'll try to find a way to test you on the pronunciation at the end. To give you, okay, go ahead, sorry.
would you use that to get rid of P as an element of natural number?
Okay.
And then use P1?
Absolutely. All right. Guys, similar lessons before. You cannot apply P1 directly because this part here is not empty, right? Okay. By applying monotonicity, we're going to get just 0 is a natural number. That one, no brainer. Just use P1. Yes.
For the second one, do you just
Yes, second one. Yes, go ahead.
it's like n with b? Like, it's like, is n equal to b?
Say it again. Sorry, I want to catch you.
Do P3 with like saying, okay, well, n is
Yeah, so for the second one, you're basically done.
Yeah.
But you have to know exactly. So somehow you want to see why is this matching this. Basically, n here is like a d here. And the n here, again, is like the d here. So that's fine. You can just use P3 directly. So you can just say P3. And just add a little bit more explanation of where n is instantiated by d, yes. Okay, the d here, which is over here. All right? Okay, awesome. Guys, are we okay with this? Adnan. Yeah.
Does it always have to be natural number? Could it be like, it's very specific.
You mean for P1 and P3? Yes. For very good. So it's two parts. Number one, for P1 and P3 and also all the piano natural number axiom, yes, they have to be natural number. Otherwise, you cannot apply them. Number one. Number two, yes, if you got some general model where you got some integer that you want to prove, you might need to use other inference rules, which we haven't spoken about yet. Yes. Okay. All right. So we got about 10 minutes, right? I would suggest we try to do a little bit of deadlock freedom. The deadlock freedom, I can give you some roadmap right away. We're going to define deadlock freedom. I'll talk about it in general. And we have to formulate a sequence. And this one, the proof is going to be a little bit more complicated even than before. I'll do that together with you on Wednesday. just to begin with. After that, we'll find that the deadlock freedom sequence cannot be proved. So again, we got to go back to fixing the model. But this time, rather than fixing the individual events, because it turns out for deadlock freedom, it really depends on all the events considered together. I'll get there. But for the deadlock freedom, to really prove it, we have to fix other parts of the model. After that, we got to regenerate the sequence and prove it again. That'll be the final bits we have to do for this initial model. Okay, let me do as much as possible for today, and then we'll continue in the beginning on Wednesday. Let's now do that. Okay, that's about initialization. And I believe every point is covered, but you guys can review the slides just to get prepared. All right, this one here we also covered. Okay, deadlock freedom. Okay, let's now go over some concept, and then we have to also talk about how you can specify the deadlock freedom proof obligation. Let's go over some bullet points. So far we have proved two things. Number one, how we can, if the system really established the invariance by using the init events. Also, we talk about how we can preserve the invariance by the model by considering all the non-init events. These are what we have done. And now we want to make sure, especially for reactive system, the system does not really deadlock. Think about what does it really mean when the system deadlock. Okay. Before I get to the rule, let's get something very straightforward to you. So we are talking about specifically about reactive system. Okay, that's what we're given. When you say it deadlock, that simply means no reaction to the user or the environments. That's the intuitive meaning. But what does it really mean in terms of our model? When you say there is really no reaction, that means no events can occur. Based on this, will you guys be able to even formulate what deadlock freedom really means? When I say no events can occur, what does it really mean? How can a single event occur if its guard is true? Now, if I say none of the events can occur, what does it really mean? Logically. No guards can pass, that means all the guards will evaluate to false. None of the guard is actually true. Agree? Okay, good. Let's really get the thinking really straight. Otherwise, you might be thinking, oh, you just give it another logical rule. I'll get to you. Give me a moment. No events can occur. That means none of events guards is satisfied.
Oh, okay.
Oh, that answer your question?
Yeah.
Okay, very good.
Not a specific predicate. Not that every predicate of every guard. Not that every predicate.
We somehow, we want to stay a predicates, which is going to consider all the guards together.
Yeah.
Okay, so guys, I'll give you two options. Okay, so I'm just trying to help you think about how you can, rather than just giving you the rule directly. Okay, so given this, right, I give you two options. So here I got the guard of ML out. I also got the guard for ML in. Okay, I got these two guards. This is a Boolean. This is a Boolean. I want to somehow combine them into another Boolean. And that Boolean there should really correspond to this guy over here. Yes?
Not in bracket. That's the ML out or GM.
Very good. Okay, awesome. Let me just write it down. I think your classmate is 100% correct. It is not the case that either this is true or this is true. So this is the precise condition when the system deadlock. Okay, let me put a little bit of comments over here. Not the case that some events is enabled. So this is the deadlock condition. Are we okay so far, right? We're starting from something very simple, and then we get to this condition here. Right? Just make sure you follow the logic here. But when we specify the proof obligation, we wouldn't say we want to prove that deadlock is possible. We'll say that deadlock free. Okay? So this is so-called a deadlock condition, which is this. And what we want to prove. What we want to prove is the system is deadlock free. And hopefully you can see that deadlock free versus deadlock, they are completely opposite, right? In terms of logical negation. So take out this negation, right? So what we want to prove is the guard of ML out or the guard of ML in. This is the deadlock free condition for our initial model. If this predicate here is actually true, that means either this is enabled or this is enabled. So the system wouldn't deadlock. It's deadlock free. All right? If both of them are disabled, in that case, the system deadlock. You want to make sure you be very clear about whether this one should be the case or this one should be the case, right? They're kind of a logical negation of each other, but you want to know which one to mention which, right? Okay, so far? Okay, let's now take a look. Okay, let's go back to the slides. And I got about 2 minutes. Let's go a little bit more slides, and then we'll try to finish deadlock freedom on Wednesday. So deadlock state means all the guards have false, right? And then when deadlock happens, none of the events is enabled. Oh, I want to show you one more thing. You remember De Morgan from the review, right? Let's rewrite this slightly. All right, this one here is equivalent to not the case ML out and not the case ML in. So when I say this condition is the deadlock condition, it's equivalent to say the following. The guard for ML out is not satisfied. And also the guard for ML in is also not satisfied. None of them is satisfied, right? They're logically equivalent. That's another way to see that. Okay, so the system is blocked and not reactive anymore. And then, so we are going to have, so this is the new requirement we introduced. So one thing to also note, we don't necessarily have to start with a fixed number of requirements. As we are trying to argue or try to verify our system, you might find that you want to add new requirements into the system. It's also possible. So this will be the new system requirements. Given that bridge controller should be reactive, so we want to say that once started, the system should work forever. Okay, so that's the new requirements we have. Right? Recap, and then I'll let you go. So today we spoke about quite many things, right? You want to make sure you really catch up, otherwise things will just get more and more demanding from you. So guys, please, this now will be the best time. Let's do a very quick recap, and then we'll call it a day. We started with reviewing what we covered before the reading week, right? From here. And then we talk about, for all the 4 sequences, how we can prove them individually. Either we can prove or we cannot prove by applying the inference rule that's applicable. Okay? And then for the unprovable sequence, we try to fix the model. In this case, by adding some guard into the events. In that case, we can regenerate all the sequence into new ones. And as an exercise, try to reprove each one of them. And they should be provable after fixing the model. And after this, we talk about something called initializing the system. You want to make sure once you initialize the system state, you can establish the invariance. That's going to make the induction complete. And these are the sequence we proved, right? Now over here. And the final bit we talk about is about deadlock freedom. So this page here is only informal, but I think that's really critical for you to know precisely what's the deadlock condition, and its logical negation is simply what's the deadlock freedom condition. That's our goal to be proved. And we're going to start from here on Wednesday. Guys, thank you so much. I'll see you on Wednesday. Thursday, I meant.